Hello, folks. So, welcome to part 20 of learning Rust from scratch. And in this video, we'll be continuing the ownership chapter, ownership section. What is ownership? So, last we were actually at variables and data interacting with clone. So, if we do not want to deeply copy, sorry, if we do want to deeply copy, because usually strings are copied in a shallow way, like this is a shallow copy. Uh, it copies only the pointer, then the length and capacity, and it moves basically over here because both S1 and S2 cannot own hello. If both uh, own hello, then when both go out of scope, how will you actually both go out of scope together, right over here? How will you actually free memory twice? Because there will be only one space used up by hello. So it just moves the ownership of S1 to S2 over here, and S1 goes out of scope basically, right? So I think that's what they've said here clearly. Um, so if you've heard of shallow copy and deep copy while working on it, the concept of copying the pointer, copying the data sounds like but because Rust also invalidates the first variable, instead of being called a shallow copy, it's called a move because it's invalidating the first variable, making it almost go out of scope or something. In this example, you would say that S1 has moved into S2. So what actually happens is shown in this. So now we look at variables and data interacting with clones. So if we do want to deeply copy the heap data of the string, not just stack data, so we can use a common method called clone. We'll discuss methods syntax in chapter 5, but because methods are a common feature in many programs, we've probably seen them before. So here's an example of the clone method in action. Right, so you can actually copy this now, and actually if I say copy this, does it, okay, it copies only this. If I say open this and then copy, it copies the whole thing now. Can I just now, yeah, copy? Yeah, nice. So now it says clone, so it will say hello, hello. So there are two hellos now. So S1 has not moved to S2 now. Instead, S1 has been cloned. So there are two hellos in the heap, and each hello is being pointed to by S1 and S2. I mean, one hello is pointed by S1, another hello is pointed by S2, and they both have their own length and capacity separately. This works just fine and explicitly produces the behavior shown in 4.3, where read data does get copied. So this is 4.3 where the heap data does get copied. Right? So when you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. Stack only data, copy. There's another wrinkle we haven't talked about yet. This code using integers, part of which was shown in listing for do works and is valid. Yes. So let's do this. Right. So, but this code seems to contradict what we just learned. We don't have to call clone, but X is still valid and wasn't moved into Y. So this is stack only data, so it just got copied. It didn't get like moved, right? And you can actually see that you can actually say Y equal to, oh, you can't mutate Y or X because you haven't said mutable. Anyways, but this code seems to contradict what we just learned. X is not moving into Y, right? And we didn't call clone, but it still has two separate values, but X is still valid um, and wasn't moved into Y. right? And we didn't have to call clone. The reason is that types such as integers, booleans, floating point numbers, characters are all on the stack that have a known size at compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there is no reason we would want to prevent x from being valid after we create the variable y. In other words, there's no difference between deep and shallow copying here. So calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Plus has a special annotation called the copy trait that we can place on types that are stored on the stack. As integers are, we'll talk more about traits in chapter 2. So integers are stored on the stack. The type implements the copy trait. Variables that use it do not move. Instead, they get copied, but rather are trivially copied, making them still valid after assignment or another. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. So if there's a drop trait in any of the parts, if the type or any of its parts, if the type has it or any of its parts has drop trait, then we can't put the copy trait. If the type needs something special to happen when the value goes out of scope, then we add the copy annotation to that, we'll get a compile time error. If the type needs something special to happen when the value goes out of scope, that is for destructuring or destructure to free up memory and stuff. And we add the copy annotation to that, we'll get a compile time error. To learn more about how to add copy annotation to your type to implement the trait, see derivable traits in Appendix C. We'll see this later. So, derivable traits, we'll see this actually later, or you can say it now. So, in various places in the book, we'll discuss the derive attribute, which you can apply to struct or enum definition. The derive attribute generates code that will implement a trait with its own default implementation on the type you have annotated with the derived syntax. In this appendix, we provide a reference of all the traits in the standard library that you can use with derive. So copy, drop, and all right. Each section covers what operators and methods deriving this trait will enable. Um, what operators it will enable and what methods will it enable if you derive this trait. What the implementation of the trait provided by derive does, what implementing the trait signifies about the type, conditions in which you're allowed or not allowed to implement the trait, examples of operations that require the trait. Partial equality, partial ordering, clone and copy for duplicating values. The clone trait allows you to explicitly create a repeat copy of a value, and the duplication process might involve running arbitrary code and copying key data. Place variable and data into that clone. Um, so this is part of the ownership, right? Variables and data into clone. Section in chapter 4 for more information on clone. Deriving clone implements the clone method. Clone trait implements the clone method, which when implemented for the whole type calls clone on each of the parts of the type. This means all the fields or the values in the type must all the fields or values in the type must also implement clone to derive clone. An example of when clone is required is when calling the toVector method on a slice. The slice doesn't own the type instance it contains, but the vector returned from will need to own its instance. So toVector calls clone on each of them, each item. Thus, the type stored on the slice must implement clone. Interesting. Type stored in a slice. Okay. Hmm. Because the slice doesn't own the type instance it contains, but the vector returned from the return will need to own its instances. Calls clone on each item. So every item on the slice it calls clone and creates thus the type stored in the slice must implement clone so that every item can be cloned. The slice doesn't own the type instances it contains. Mhm. Something to check out read. The copy trait allows you to duplicate a value by only copying bits stored on a stack. No arbitrary code is necessary. See the stack only data copy. In chapter 4, for more information, the copy trait does not define any methods to prevent programmers from overloading these methods and validating the assumption that no arbitrary code is being run. That way, all programmers can assume that copying a value will be very fast and cloning a value will be slow. You can direct copy on any type whose parts will all implement, or whose all parts, or whose parts all implement copy. A type that implements copy must also implement clone because a type that implements copy has a trivial implementation of clone, which is this copy. It performs the same task as copy. Copy trait is really required. Types that implement copy have optimizations available, meaning that you don't have to call clone, which makes the code more concise. Everything possible with copy you can also accomplish with clone, but the code might be slower or have to use clone in cases. Hmm. So, what types implement the copy trait? You can check the documentation for the given type to be sure. But as a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation or is allocation in heap or some form of resource can implement copy. Here are some of the types that implement copy. All the integer types, such as unsigned third of bit, integer third of bit, unsigned integer third of bit, and then 64-bit, and then architecture size. U size, I size. The boolean type bool, the value is true or false, true and false. All the floating point types, such as FP64, that's floating point 64 bit, and then floating point 32 bit. The character type tuples, if they only contain types that also implement copy. Uh, for example, I32 implements copy, but I32 constant does not implement copy, it implements clone, I think. Ownership and functions, so let's look at that. Um, The mechanics of passing a value, basically an argument, into a function, are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy just as assignment does. So, yeah, so similar to assigning, so similar to those when assigning a value to a variable. So, passing a variable to a function. So, if the variable is a string, capital S string, so it's like a string type, then it'll move. If it's a scalar, if it's on the heap, it will move. If it's on the stack, it will copy. This as an assignment does. Listing 4G has an example with some annotation showing where variables go into scope and out of scope. So function name and string s. So s, this is a heap. This is a literal stack, but this whole thing is a heap. Take ownership. So s. So it moves. So the string equal to the string and moves here. So this one takes ownership. And this one here, the value of s has moved to some string. Some string comes into scope. Some string goes out of scope, and drop is called the banking memory is free. So here, if you tell s or something, s's value moves into the function, and so is no longer valid here. X comes into scope, makes copy x some integer, and then say some integer comes into scope. Because out of scope, nothing special happens. Because I influence the copy trait, it does not move into the function, so it's okay to use the X after the. If we try to use S after the call to take ownership, this us would throw a compile time error. These statistics protect us from mistakes. Try adding code to main that uses S and X to see where you can use them and where the ownership rules prevent you from doing so. So let's just completely do that. So hello 55, so we can actually do even this. Can you do something like some integer plus equal to 5, right? If you say it's not mutable, okay, 22, Okay, so cannot assign to immutable argument. So let's make it as a mutable argument. Yeah, so here you can see that it's copied and it's a mutable copy. So it's copied, file is copied into this, but it's mutable, so it's just make it as 10. You can say sum underscore integer equal to sum underscore string equal to x equal to y. So, yep. And then if you try to call s over here, print line s equal to s. So add semicolon. So move occurs because s has fetch string, which does not implement the copy print. S value moved here, value borrowed here after move. So yep. Consider changing this parameter type in functional to borrow instead of owning. So instead of owning, so here ownership moves, right? So here it says ownership moves, and then you're borrowing the value to print here. Instead, you should just borrow the value. Let's see how print is implemented. Okay, I can't look at it here. Let me. Anyways, I'll probably. One moment. Execute this program and direct out of bounds. Let me try to open this up and let me go to learning Rust, visuals, and here if I just say print line and open this up, we'll actually see. Hmm, I think borrowing is a tricky thing. This pay and then standard library print it does format arguments and then I don't know what how that works. But anyways, um, let's just close this for now. Thing is, looks like if you can just, it says this error originates, so it says this parameter takes ownership of the value. Consider changing the parameter type in function takes ownership to borrow instead of copying the value. Uh, instead, if owning the value isn't necessary, do you really need to own the value? How do you make it as like borrow? I don't know. See, and then some string. So this parameter takes ownership of the value. This error originates in the macro, which comes from the expansion of the macro. This uh, consider cloning the value if the performance cost is acceptable. So you can just do clone, right? SS value moves in, so you can just clone like this, or uh, so basically it happens here. Value borrowed here after move, and this error originates in the macro. So I believe the error is originating over here inside this. It's trying to own it, I think. Instead of, or it's trying to borrow, sorry. Value borrowed here after you, so after move. So, yeah. So if we try to use a supplement, so Rust would throw compile the error, these targets, so it's clear from here, right? If you just put S over here, Rust would throw compile the error. So have to take ownership here. And these statistics protect us from making mistakes. Try adding code to main that uses S and X to see where you can use them and where the ownership rules prevent you from doing so. And so I don't have any problem in using X, but before X, it will be out of scope, so I can't use it. Everywhere else you can use X. Here also I've used X, so it's fine. And return values and scope. Returning values can also transfer ownership. Listing 44 shows an example of a function that returns some value with similar annotations as those in listing 43. So it says gives ownership, moves its return value into S1. Um, so and then S2 comes into scope, takes and gives back S2. So it takes S2 and then gives back S2. Is returned and moves out to the calling function. Interesting. Let's try this out. Copy. I'll just put this as this. Instead, I'll just comment out this alone. Anyway, so now I'll just put this function main. So it says let S1 and gives ownership. So basically, this creates a string and then gives back the ownership to that array. So let string from and then you return. This is an expression, not a statement. Statement uh, is where you assign stuff and whatnot. An expression has some value. A statement does not have a value. Um, I remember doing that a bit before, anyways. And this is the last expression and last thing, so it just gets returned. You can also say return, I think. I think you can say return. Yeah, but let's not do that. So some string is returned, some underscore string is returned, and moves out to the calling function. So here you cannot just do print again, however it gets returned here. So it doesn't make sense to print anything. If you print actually something over here, it'll be an error, I think. Some underscore string. Let me try to run, and it will give an error, I think. Okay. If you put a semicolon, that's all. It's a statement. So expected this, unexpected token. I think the LBA expected here also this way. Expected string found unit basically. Like this is a statement, and I put unused variable. Okay, there are some unused stuff. This is a statement. You don't even need to put a semicolon here. I think this is a statement, and it does not return any values. Or this is a if this is a statement, it does not return anything. If this is an expression, it does not return anything because this print line function does not return anything. So it gives unit or the empty tuple. So it says expected string. So if you just put statement and you say expected string, and it returned nothing. So expected string found implicitly returns unit or empty tuple as its body has no tail or return expression. The tail is basically this. So the tail is this, and we should remove the semicolon or else it gives ownership. So there's no return, there's no tail also. The tail is basically an expression, last expression. So if you do this, it gives ownership, right? S1. We don't use S1 though, unused value variable S1, and then we have S2. S2 it takes and gives back, so S2 comes here. So a string comes in the scope, a string is returned and moves out to the column function, right? So you can actually print stuff over here. So let's say, and this is by reference, we can actually see it also. Moves its return value into S3. So we can actually see um, print ln and say S3 equal to S3 and you can say yeah, something like that. Oops. S1 and then S1, S2 and S3 and here you can actually say some string, right? And here you can actually say uh, a string, a string, and you can actually even change it string But this is not a mutable string, I think. Let's see. Oh yeah, you can do actually push string, I think, and then say world, and then say again this, and then let's see how that goes. So it says found print line. Let's put 39 here. We need to put a semicolon, and then it should just work. Cannot borrow as mutable. Okay, so you're trying to borrow as mutable. This is a normal borrow, mutable borrow. You can just say mutable, and I think it says some string is yours, S1 is yours, S2 is hello, A string is hello, and then hello world, and then S3 is hello world, right? So this is a mutable borrow. If you don't want to mutate, then you just normally borrow, right? So when you get a string or some similar type where copy is implemented, it's called a borrow and it's not a copy, right? And it is not moving per se. And if it is moving, I mean, it is actually moving and it's borrowed. So in this case, it's actually moving and then going back. So it takes, that is moves, and then it goes back also. It moves back, right? So um, interesting stuff. So yeah, I wonder how the print line is implemented, but yeah. So the ownership, so here if you see the ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. So in this case, it moves it only when there is a copy trait, or sorry, more like one moment, which has a drop trait basically, which has a clone, right? Um, So if it has a copy trait, it's basically on the stack. But if it has a drop, it's basically on the heap, right? So the ownership of a variable that is on the heap follows the same pattern every time. Assigning a value to another value moves it. When a variable that includes, unless you do a clone, right? Simply assigning this moves. When a variable that includes data on the heap goes out of scope, um, the data is like dropped. The value will be cleaned up by drop unless ownership of the data has been passed on to another variable, has been moved to another variable. While this works, taking ownership and then returning ownership by with every function is a bit tedious. What if you want to let a function use a value but not take ownership, right? So because string, we just wanted to use the value but not take ownership. Like you can't take ownership, you can just use it. Should we just clone it? No, it's quite annoying that anything we pass in also needs to be passed back if you want to use it again. In addition to any data resulting from the body of a function that you might want to return as well. Rust does let us return multiple values using a tuple as shown. So returns the length, calculate length. But this is too much ceremony and a lot of work for a concept that should be common. Like you just want to get the value of it. I mean, you just want a reference to it. You don't want ownership to it. You just want a reference. Or you just want to borrow it. So it should be it should be not be a lot of work, and it should be a concept. Uh, and it's a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership. That's called references. Right? References and borrowing. So this one I'll probably do it in a separate video. And that's all I have for this video. I'll see you next one. Bye bye.